Okay, let's discuss elementary phase behavior of a pure hydrocarbon. An example of a behavior of a pure hydrocarbon as pressure and temperature are varied. Consider the case of ethane, C2H6. Suppose a sample of ethane at 400 psi A and 60 degrees Fahrenheit is contained in a cylinder having a movable plunger. Under these pressure and temperature conditions, ethane is a gas. If the plunger is slowly forced into the cylinder so that the pressure is increased at constant temperature, the gas begins to liquefy at a pressure just less than 500 psi. And it is possible to move the plunger into the cylinder without any further increase in pressure occurring. This continues until all of the ethane is in the liquid state. And from that point, large increases in pressure, only small decreases in volume. Okay, let's look at slide number 1. From slide number 1, you can see that we are plotting pressure in psi against volume of ethane, which is in cubic feet. If you look at where we start, labeled as A, and we begin to move the plunger in, reducing the area, the gas becomes compressed and moves to point B. As you can see, pressure at this point is increasing. On slide 2, you can see that once we reached point B, we hit what's called the dew point. The dew point is where the first drop of liquid appears. At this point, we continue to move our plunger in, which reduces the area, which compresses the gas, and as we move it toward C, more and more liquid appears and less gas appears. One thing you will notice, the pressure does not increase. We change from gas to liquid, but the pressure does not increase until we hit point C. C is the bubble point. The bubble point is the last point where any gas exists. Beyond C, only liquid exists. And as you can tell from slide 4, it is very difficult to reduce any volume at this point, but as we try, pressure increases rapidly. Now we will heat the cylinder and withdraw the plunger until the sample of ethane is at 400 psi and 110 degrees Fahrenheit is obtained. Evidently, the ethane will be a vapor at these conditions. Once again, force the plunger up into the cylinder and record the pressure. In this case, a curve similar to the one that you see above is obtained, and the outstanding features of this is that there is no sharp change in the shape of the curve. In other words, no dew point and no bubble point are discernible. Repeat the process time and time again. However, with a temperature of 110 degrees Fahrenheit, the curve is going to be the same. No dew point and no bubble point. From this graph, you can see that the temperature of 90 degrees Fahrenheit and a pressure of 709 psi is known as the critical point. When a temperature is below the critical temperature of 90 degrees Fahrenheit, ethane may exist as a liquid alone, as a gas alone, or as a mixture of the two. When the temperature of ethane is above the critical point, there is no sharp demarcation between gas and liquid, and no pressure at which gas or liquid exists simultaneously. Similarly, for the critical pressure at 709 psi. Now let's consider a mixture of hydrocarbons. It is found that a pressure-temperature relationship can no longer be represented by a simple vapor pressure curve. Inside the envelope, gas and liquid can exist in equilibrium. The composition of the gas and liquid and their percentages being dependent upon the pressure and the temperature. Outside the envelope, the hydrocarbon mixture is in one phase. The liquid phase exists at the lower temperature and higher pressure, and the gas phase exists at higher temperature and lower pressure. In order to understand the hydrocarbon of the hydrocarbon mixture better, and in order to see what happens to the critical point, consider three gas samples, each at P sub 0. The temperature of the samples being T1, T2, and T3. Let the pressure of each sample be gradually increased, the temperature being held constant. For the first sample, liquid begins to condense out at point B1. This is the dew point, and go into the solution until at point C1, the bubble point, the final gas traces disappear at high pressure. The hydrocarbon mixture is a liquid. Such behavior typifies the normal oil field. The initial pressure in the field is either above or below the bubble point pressure. In the former case, only liquid is present in the formation, and the oil is said to be undersaturated. In the latter case, both liquid and gas, or gas and oil, are present in the formation, and the oil is said to be saturated. As production is taken from the field, it is initially undersaturated. The point C1 will eventually be reached as the field is produced. The corresponding pressure is known as the bubble point or saturation pressure, P sub B. From that point onward, more and more gas is evolved until finally, at abandonment of the well, the pressure is at the same point between C1 and B1. Okay, let's look at case 2. Liquid again commences to form at the dew point, B2, and the percentage of liquid starts to increase as the pressure rises. But instead of this process continuing, it is found that further increases in pressure cause the liquid to re-vaporize, so that by the time C2 is reached, the last traces of liquid are just disappearing. At a higher pressure, the fluid is gaseous once again. Thus, C2 is also a dew point. Such behavior typifies a condensate field. As the pressure is reduced by producing the field, liquid begins to condense out of the formation, and this is a phenomenon known as retrograde condensation. If the reservoir pressure can be reduced significantly, this condensate may re-vaporize, but one of the chief dangers in condensate field production is that the liquids will be left in the formation at the time of abandonment. You see, any liquid forming in liquid saturation less than critical will not move. In order to prevent the loss of condensate in such reservoirs, engineers will typically strive to maintain pressure by recycling dry natural gas back into the formation. In case 3, we'll see that no liquid phase is formed no matter how high the pressure is raised, so that a field containing a hydrocarbon mixture operating on such a line would produce dry gas without any condensate problems. Such behavior typifies a dry gas field. In conclusion, it must be mentioned that each hydrocarbon mixture, each naturally occurring gas or crude oil, will have its own pressure temperature envelope. So the situation is not quite as simple as looking at this one graph.